In this lecture, we're going to go over Lewis structures. This is another topic that you've hopefully seen before, but we do a lot of structure drawing in organic chemistry, so you need to make sure that you're really good at Lewis structures. When you're first starting out to draw Lewis structures, I recommend that you follow the following steps that we're going to go over. Once you get really good, you won't need these steps anymore. Hopefully you're just doing it really quickly in your head. Let's say you're given the molecule H4C2. First, you want to count the total number of valence electrons in the molecule. There are 2 carbons. Valence for carbon is 4. So 2 times 4 equals 8. And we also have 4 hydrogens. Valence for hydrogen is 1. 1 times 4 equals 4. So our total valence for this example would be 8 plus 4, or 12. Next, you want to try writing a skeleton of the molecule with only atoms and single bonds. You might have to do this a couple of times before you get something that makes sense. For example, if you just wrote it out as H, 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 C, C all in a row, hopefully you instantly recognize that you've got a hydrogen here with 2 bonds. That's no good. So try this again. One tip is to try to put your carbon atoms in the middle. So if you try something like this, that's going to be much better. We've got carbons in the middle. We don't have any hydrogens that have way more bonds than they need to. Okay, next, we're going to subtract 2 electrons from the amount we determined in step 1 for each bond in the structure. So we have 1, 2, 3, 4, 5 bonds. That means 2 electrons per bond. We need to subtract 10 from 12. 12 minus 10 gives us 2. So we have to distribute these remaining 2 electrons as lone pairs. Okay, let's try throwing those electrons on over here. Next, if there is an atom that does not have a filled valence, convert a lone pair from a neighboring atom to a bond. So let's look over here, and you'll notice that our carbon on the right doesn't have its valence. It wants a valence of 4. It also, if you'll notice, is an octet rule violator, so that's no good. So let's erase those 2 lone pairs there and convert that to a bond. And now you'll notice we have a valid and happy Lewis structure. We don't have any charges. We have no octet rule violators. Everything has its valence, so this is a good solid Lewis structure. If for some reason you've gotten to this step and you found that you do have octet rule violations or lots of charges or both, go back to step 2 and redraw your skeleton. So remember that first skeleton we drew out, that for example would be horribly wrong and we'd want to try again. As I mentioned when we were talking about formal charge, there are certain bonding patterns that you want to look for so that way your molecules don't have a formal charge. Carbon, for example, prefers to have 4 bonds and no lone pairs. And so you can see 4 different ways that we can get carbon to do that. So carbon can have 4 single bonds, or it can have 2 single bonds and a double bond, a triple bond and a single bond, or 2 double bonds. Those are all possible patterns. And you can see here that there are 3 different ways for nitrogen to bond and be happy, meaning have its formal charge, have its valence fulfilled, and have its octet fulfilled. You can also see some examples here for oxygen and for our halogens. Our noble gases, as you can see down here, really don't like to bond, so we're not going to worry about them too much. They really prefer just having those 4 lone pairs. Let's walk through another example. Let's try CO2. Our total valence would be 4 plus 6 plus 6, or 16 total. So let's write out the skeleton. We're going to subtract 2 electrons for each bond. I have 2 bonds. So 16 minus 4 equals 12. Now I need to distribute the remaining electrons as lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now if you're looking at this, we've got some unhappy things going on. Carbon, for example, doesn't have its valence. Let's try moving some electrons around. Let's move those 2 over here and form a double bond. That still isn't super helpful because now we've got a situation where this oxygen is going to end up with a +1 charge. This oxygen over here is going to end up with a -1 charge. And I promise you that you can keep moving electrons around all day and you're never going to find a happy situation here. So let's go back and try again with a different skeleton. Remember what I said about keeping carbon in the middle? So let's try that. So now we've got 16 minus 4, which is again 12. And let's distribute them around here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In this case, the oxygen on the left here doesn't have valence. So let's move a lone pair around. Okay, so that makes that left oxygen happy. And now how about this right oxygen over here? Let's move that lone pair and make a bond on the right. And now if you look at this molecule, oxygen is neutral, formal charge of 0. Carbon has a formal charge of 0, and the oxygen on the right has a formal charge of 0. So everything is happy, everything has its valence, and no formal charge. So this is the correct structure. Let's do one last example. NH3, valence for nitrogen is 5, plus 3, 1 for each hydrogen, gives us a total valence of 8. When you're drawing out a possible structure, remember to put nitrogen in the middle. If you try to put all those hydrogens in a row, you're going to see that the hydrogens are going to have more than one bond, and that's bad. We have 3 bonds, 1, 2, 3. So we're going to subtract 2 electrons for each bond, which would give us 6. 8 minus 6 equals 2. And we need to distribute the remaining electrons as lone pairs. So that means we have 1 lone pair. And if you do a quick check, nitrogen has its octet and it has a formal charge of 0. So we're all good. This picture from your textbook has some examples of proper Lewis structures. We've gone over most of these, but here's a quick recap. Hydrogen, of course, brings 1 electron. So if you have 2 hydrogens, those form a bond. Carbon has a valence of 4. Plus 4 electrons, 1 for each hydrogen, gives us 8. Each carbon-hydrogen bond gives us 2, 1, 2, 3, 4, 5, 6, 7, 8. So carbon has a formal charge of 0, it has an octet, and it meets its valence. With CO2, carbon again has a formal charge of 0. Carbon brings 4 electrons, each oxygen brings 6, and you'll see that what we've done is we've distributed those total electrons around the whole molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And in NH3, nitrogen brought 5, each hydrogen brought 1, 1, 2, 3, 4, 5, 6, 7, 8. We're not going to go into too much detail, but I did want to address the fact that sometimes you will have octet rule violations in proper Lewis structures. One example is BH3. You'll notice that boron brings 3 electrons to the table, and each hydrogen brings an electron. So that's 6 electrons total, meaning that there's no way in this situation for boron to have its octet filled. And this is just what happens because there aren't any other electrons to play around with. You can also have situations where you have expanded octet, meaning greater than 8, and that happens, for example, in sulfur. But we're not going to deal with these examples too much in organic chemistry. For the most part, you're going to be dealing with carbon, nitrogen, oxygen, and hydrogen. So you're always going to be looking for a fulfilled octet. That wraps up Lewis structures. Please practice a lot with Lewis structures until you can basically do them in your sleep, because we're going to build on this heavily in subsequent videos and in subsequent chapters.